get started. I know we've been saying this a lot, but today we got a lot to cover. So let's get the cameras on. All right, so today we're going to start talking about the next two chapters, 9 and 10, are highly related. And this is almost the opposite of the last chapter. In the last chapter, we had really no new material covered, but in fact, we had to learn how to use the material we've learned in previous chapters much more in a much more sophisticated manner than we've done it before. You know, to be able to solve those combined loading problems really require that you really fully have a good understanding of torsion, axial, bending, transverse shear, and what they mean physically. Okay, but there really was nothing new going on. Now, in chapters 9 and 10, we're going to actually do something that's conceptually new. It's a different way of thinking of things, and it's a little bit abstract. Sometimes it gets a little confusing, but the fortunate thing is actually to solve the problems, they tend to be rather plug and chug. So you know, you can pick whichever way you like better, right? But it is what it is. All right. So again, could you guys turn on your cameras to make my life easier? All right. So chapter 9. Let me just share my screen here if I can. All right. So chapter 9 is the topic of the title of the chapter is stress transformation. Okay. Let me do this. And let's go. Oops. Okay. So stress transformation. And we'll talk about what we really mean by stress transformation. But suffice to say, actually, depending upon what orientation you look at the state of stress, you'll get different stress components. But obviously, it fails or it doesn't fail, right? So the topics that we're going to talk about this chapter is we're going to figure out how we do stress transformation in a plane, so planar stress transformation. We're going to do those two ways. One will be using sum of forces on free body diagrams, and then there'll be a set of equations that basically do the same thing but kind of make it a little easier. I am not going to derive all the equations as I have done in the past, just because we're a little bit behind and we do need to get to beam deflection and that sort of stuff and column buckling. So a lot of the derivational stuff will be flipped. Even using the sum of forces, I won't do to the full degree that I do normally. But there are example problems online that I've worked through that do that already, okay? Because, in fact, I think if you can understand the concept, using the general equations is probably going to be preferred, okay? So this material here, we're going to say is flipped, right? All right. Likewise, with Mohr circle, I derive Mohr circle, but, you know, I don't really think it's really necessary. I have a PDF with the derivation as well as a video, I think. So this will also be flipped. I'll just show you the equations and how this works. So you're going to actually have three ways of doing the same thing. But Mohr circle is a really nice graphical approach that allows you to easily do the next three items, which is talk about the principal stresses and specifically the state in which we have a principal stress state, maximum in-plane shear stress, as well as maximum absolute shear stress, okay? Chapter 10, we're going to do the same stuff, but it's going to be with regard to strain, so it's almost the same, all right? All right, so what do I mean when I talk about plane stress transformation? Okay, so down here you got a little picture. This is a structural finite element model of an airplane fuselage, right? So I've kind of pulled out one of the bulkheads, all right? And let's see what else we got here. So if you were to look at a point on that bulkhead, right? And we've seen this actually already when we talked about some of the combined loading problems. Let's say you do either a finite element analysis or you can do it by hand. You get a state of stress. There it is. There's a planar state of stress. We have a normal stress in the x direction, in the y direction, and an in-plane shear stress, okay? This state of stress is with respect to that XY coordinate system. Now, we can also consider an alternate coordinate system, x prime, y prime. And if you look at that, this is kind of like a polar coordinate system, where this would be the angle theta, and then you'd have a radial direction. So this is kind of like what we would normally call the radial direction, and this would be like the theta direction. If I did it this way, this would actually be the theta direction, okay? And of course, you would have a different coordinate system if we're considering it to be polar at every point around the bulkhead. Now, if we look at the same exact point, you can get a different set of stress components in that x prime, y prime coordinate system. So if we look at it in the radial and the tangential directions, you will get different numbers here than you will get here. All right. Will they fail at different loadings? Of course not. The material is still seeing somehow the same amount of strain energy in there. They'll fail at the same point, but the numerical values we call sigma x, sigma y, or tau xy, they're actually different. But clearly they have to be related. Somehow there is some aspect of this that is invariant as we look at it in different coordinate systems. So for example, if you had a failure law, if you had some rule that predicted when the material would fail, if you put in these components, you better get the same answer if you put in these components. Because if you don't, then your failure law makes no sense, because you're saying, okay, if we look at it in terms of x and y, it'll fail. But if we look at it in another coordinate system, it won't fail, which is obviously completely nonsensical, because the aircraft doesn't know boo about coordinate system. The aluminum in that bulkhead doesn't know anything about the tensor transformation, right? So there's something that's still related to these regardless of what coordinate system we look at this. And that's the idea of stress transformation, okay? So obviously these things have to be related, and how do we do that, okay? Does that make sense? So it's not like we're rotating the material. The material is not changing in any way. The loading on the material is the same, but we're just looking at it in a different coordinate system, and we get different stress components as a result, okay? And that's kind of what's showing here. So if we looked at this state of stress, okay, and let's say we wanted, and we knew these components, we knew all the components here, and let's say you now want to get the components in this state of stress, right? So we know x, I'm sorry, not x. You know sigma x, sigma y, and tau xy, and you're given, obviously, this angle theta, the new orientation of the coordinate system. We want sigma x prime, sigma y prime, and tau x prime y prime. Does that make sense? We want to be able to figure out what should be the components in this new coordinate system. Obviously, they have to be related to the components in the other coordinate system because it's the same physical situation, all right? So one way we can do that is if we look at this free body diagram here, or I should say, like if we take a cut like this, where this angle here corresponds to the rotation angle theta, right? So this cutting plane here, if you will, is in a sense, it's parallel to this face. Does that, right? And that's what I'm showing down here. So if I do that, that is going to expose a normal and a tangential force on this face here, this cut face, that has to be related to the stress components here in the new coordinate system. And that's exactly what we're doing here. So this is a free body diagram. All right. And you can see here, I am not writing sigma x prime, but I have the stress component sigma x prime multiplied by the area. So delta A is this area here. That's the area of that face, okay? So this is actually, that is a force, right? That's the force, the net force of the sigma x prime normal stress acting on this cut face. Likewise, this is the net force from the tau x prime y prime acting on that face. And we have the same here, 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 and here. This cosine comes into play because if this area here is delta A, the area on this face is delta A cosine theta. Likewise, the area of this face would be delta A sine theta, right? So I apologize for writing all over this, but you can see what I'm doing here is taking the stress component and multiplying it by the area at axon. So all those are forces, right? And so this is a free body diagram where you can then do sum of forces in the x direction equals 0 and sum of forces in the y direction equals 0, or sometimes it's easier to do them in terms of the x prime and the y prime direction. It really doesn't matter, okay? And so from this, you get two equations that will allow you to solve for our unknowns, at least on this free body diagram. What don't I know? I don't know sigma x prime or tau x prime y prime. But here I have two equations that I can use to solve for sigma x prime and tau x prime y prime. Does that make sense? So like I said, I won't go through all the derivation. I'll do an example in a second where I'll do it on one face, but it gets a little bit tedious after a while, okay? Once, you know, it's easy to make little sign change errors, and you have to remember which angle is sine and which one's cosine and all that. But, you know, let's not get too bogged down in those details for lack of time. I have examples that do all that stuff. It's in the book as well. And like I said, the direct equations actually probably are an easier way to do this, I'll be honest with you, okay? All right? Okay, so we have sigma x prime and tau x prime, but I don't have sigma y prime. So I can get that, I believe I have it on the next slide. The same problem. Oh, I'm just doing it right here. Oh, okay, this is going through all the details. Oh, this is kind of cool. All right, so I could get sigma y prime if I were to look at a cut perpendicular to that, say like along this face. And I were to do the same process, but with a cut like this, all right? And if I did that, that would expose on this face sigma y prime. So I could solve for that, okay? So it's like two free body diagrams. All right, let me do the next slide because this kind of shows exactly what I'm talking about. So same thing, we know everything here, and I want to get the components in this one. I know sigma x, sigma y, tau xy. I know the angle theta. and I want to be able to get sigma x prime, sigma y prime, and tau x prime y prime in the new coordinate system. All right, so we take a cut like that, where this angle here is theta. All right, there is this free body diagram. Okay, so here's theta. This area here is delta A. All right, now I hope the next button pushes the other areas. Okay, if that's delta A, the area on this face here is delta A cosine theta, and on this face, delta A sine theta, because the thickness coming out of the page is the same. It's like unit thickness, if you will, right? All right. Those are the tractions, the shear, the stress components on that face. Sigma x prime, tau x prime y prime. I want to find those. But this is going to be a free body diagram. So I need to make those forces. So I have to multiply those by the area that they act on, the delta A. All right? Okay. Now, on the next face, you can see those are the tractions here, multiplied by their areas, and same down below. And so now these are all forces, and I can then do sum of forces on this, all right? Is there any questions on that? I apologize for doing it this way without numbers, but it's a little bit faster, okay? But I think you can understand the concept, right? So these are forces, not the stresses, right? And then you can see every term is going to have a delta A. So they're just going to cancel out. You know, they all cancel out. It's kind of neat, right? And I think I do. What's this? Oh, okay. Here are the actual equations. Oh boy. So yeah, I go through all this. Well, these slides are on Blackboard, right? So if we want to start doing sum of forces in the x prime direction, right? In this direction. So we're going to do sum of forces in the x prime direction. Oh, it's doing its own thing. Why is it doing that way? Okay, in the x prime direction. So let's start down on the bottom face here. So we have, oh, I'm sorry. X prime direction. Excuse me. X prime direction is this way. Well, you know what? I think this should be a y prime direction. Let me just make sure. Yeah, you know what? This is a typo. This should be a y prime. So if we do sum of forces in the y prime direction, this way, that's what that is, right? And this is x prime. Okay, so if we do sum of forces in the y prime direction, and let's start on this face here. So this is the force in the y prime direction, right? Then we go look at this face here. In the y prime direction, we have this component, right? Which is sigma x delta A cosine theta. Fine. That's the magnitude of the force. But we need to get this component. This angle here is theta. So we have the additional sine theta. Then we do the same for this component here. So we need also this component, right? So its stress is tau xy delta A cosine theta. It acts in the negative direction. And then this component here, since this is theta, we have an additional cosine theta on there, right? And you can go do the same thing on the bottom face, and we kind of repeat the process and get it on this face as well, okay? So this is an example of a sum of force in the x direction, okay? All right. All right, let's do it really quick on this one. I'll just do one of the faces with actual numbers, okay? So this is example problem 9.1 in the book. All right. And this will make it a little bit easier. All right, so here we have a airplane fuselage. There's a little differential element of material located here, and we're given the stress state in the XY coordinate system, right? So this is X and this is Y, if you will. And they want us to find the state of stress in this rotated coordinate system given by the cut lines A and B, all right? So we can think of that as an X prime and a Y prime. So we want to get the components in, oh, what's going on? Okay, I got to write this all out. So we want to actually get the components in something that looks like this. All right, where this is going to expose sigma Y prime. There and there. Sigma X prime here. And then the shear stresses. Those are the tau X prime, Y prime, right? And we know that the angle here is 30, right? So we're rotating by 30 degrees. It's a little tough to see, but right? So this angle here is 30 degrees, okay? All right, so let's do one of these, okay? So let's look at the cut along line AA, okay? And so if we do that, what do we have? We have a free body diagram that looks like this. Here's the bottom face. I'm going to exaggerate the 30-degree angle so it's easy to see, you know, what angle is 30 degrees, all right? So this here corresponds to this face. So down here, I'm going to draw the stresses for now, but then I'll change them into air forces, right? So we have the 50 megapascal stress acting down there. I'm going to drop the units in a little bit just to save my writing. And we also have the 25 megapascal stress acting there, the shear stress, right? This face here has an area of delta A. And since this angle here is 30, right? This face here has an angle of delta A sine of 30, or in other words, delta A on 2. And this face here is going to have an area of delta A cosine 30, right? Which is rad 3 on 2 times delta A. So this, to become a force, is going to get multiplied by rad 3 on 2 delta A. And this one is going to be rad 3 on 2 delta A. On this face here, I'm going to have the exposed normal stress in the Y prime direction, and it becomes a force by multiplying it by the area it acts on delta A. And likewise here, we have the shear stress tau X prime Y prime delta A. And then on this face, I have that normal stress, which corresponds, actually it's compressive, so I should do it this way. So that is the 80 megapascals times delta A on 2. And then the shear traction, which is acting up, is the 25 delta A on 2. And this is why I always hate doing this derivation. It's hard enough doing this on the blackboard, but doing this stuff on these silly little screens is really hard because there's just not enough room. All right, so there we go. So now those are all forces, right? And now we're going to do let's do sum of forces in the y prime direction, okay? So that's in this direction here. And the reason we do it in the y prime direction is because, you know, we want to find this component and this component, and they'll only show up once. If you do sum of forces in the x and the y direction, you certainly can, but the sigma y prime will show up multiple times. And it's just, you know, it's just algebra, right? So you have two equations with two unknowns, as opposed to each one of these is going to give one equation for solving for the one unknown. So it's just a little bit of a savings from an algebra standpoint. But you can certainly do sum of forces in the x direction and the y direction, not the x prime and the y prime. It just makes it easier to do that way. All right. So, okay, fine. So let's do it in the y prime direction. So I have sigma y prime delta A. Okay? Got that one. All right. Let's go to this next phase. Both of these have a component in the y prime direction. So let's look at this force here. So in the y prime direction, it's this component, right? We want this component here. This angle here is the 30. So that's going to be a sine 30 multiplied by this. And that's in the positive direction. So that's going to be positive 80 delta A over 2 times 1/2, or over 4. So that's, we got this one. Now let's do this component. It's going to have a component in the y prime direction. It's there, right? And this is where it gets a little harder to see. This is the angle. This is the 30-degree angle there, right? So this is a cosine component, and it's acting in the positive y prime direction. So it's a positive. So positive 25 delta A on 2. That's the force times cosine of 30. Rad 3 on 2. All right. So we got the components on this face and on the back left face. Now let's do the bottom face. All right. And now you can see why this gets really tedious. Okay. So in the y prime direction, let's first look at this one. So in the y prime direction, we want this component. That's the 30-degree angle. So it's going to get multiplied by cosine 30, or 1/2, but it's acting in the negative direction, right? It's pointing in the opposite direction. So it's going to have a minus. So it's going to be minus 50 delta A rad 3 on 2 times times sine of 30, which is another 1/2. So this gets multiplied by a 1/2. And then we have this last component. We want to get, that component there. So that is here's the 30-degree angle on this angle. So this gets multiplied by an additional sine of theta, or 1/2. I'm sorry, this is a cosine. Ugh, I always screw this up. This one gets multiplied by cosine. Here's 30 cosine. So I get an extra rad 3 on 2 on that one, right? And then this one it's the sine component. And it's acting in the positive direction. So it's positive 25 delta A rad 3 on 2 times sine. So that's an additional 1/2. That's the sine component. All that goes and equals 0. The delta A's all cancel out, right? And that leaves us with sigma y prime equals, I'll put everything onto the right-hand side. So 80 divided by 4 is 20. Then 25 divided by 4 times rad 3. And I have to make this a minus, excuse me. It's almost impossible for me to do this and not make an algebra mistake. I'm so bad at doing algebra. That's sort of math. 25, enter 4 divide. So this component here becomes 10.8. So I get a minus 10.8. This one here, all right, 54 divide 3 times, because I got 2 radical 3's there. This becomes 37.5. It's a negative, and then I swing it over to the right, I get positive. And then finally, this one's going to give me a negative. This is another negative 10 here, right? 10.8. And so that gives me that sigma y prime, and I hope I did this correct. There it is. Okay, I get negative 4.1, which is, yeah, that's the right answer, actually. Oh, I did it right. Amazing. Okay, I never get these right. All right, so I didn't screw anything up. So that's the answer there, okay? All right. Now you could do the same thing. I'm going to erase this, okay? Because I don't have another slide, I think, that does this. I should do this on another slide. But I'm going to just show you the free body diagram. So I could do that. This would give me, so I got from sum of forces in the y prime direction, it gave me directly the normal stress in the y prime direction. If I were to go and now do that in the this online stuff is really awful. So, okay, so now if we were to do sum of forces, same free body diagram in the x prime direction, equal to 0. So we were going to do that now. So that's in this direction. Oops, I'm sorry, the other way. This way. In this direction, right? That's my x prime direction, right? Right there. Do the same thing, okay? So what we're going to show up here on this face, on the cut face, obviously the sigma y prime doesn't show up. I get a tau x prime y prime. I'm going to drop the delta a's because it's going to come out of every term, right? And that goes in the negative direction, so there's a negative there. If we go to this other face, now you see this is why I hate doing this on these little pads, because this is completely illegible, right? Ugh. So if we were to do this component in the x direction, you would have this value here, which is a sine, and it's in the negative direction. So you'd get negative 25 over 4. This component here, it would be a cosine, and it's in the positive direction. So I get plus 80 over 2 rad 3 on 2, right? On the bottom face, this component here gives me a sine, so it's another 1/2, and it's going in the positive direction, so it's plus 25 rad 3 on 2 times 1/2, and then the traction component on the bottom, which I just did. Oh boy, I did this. I was talking to it. The traction component on the bottom is this one going in this direction. That's a cosine. So it's 25 rad 3 on 2 times rad 3 on 2. And it's going in the positive direction because it's that way, right? Yep. And then for this one, I get a sine, and it's 50 rad, and it's going in the positive direction. So it's plus 50 rad 3 on 2, 1/2 equals 0, right? And you can solve all this out, and you would get that the x prime, y prime component is hopefully minus 68.8 megapascals, right? So now we have this component and this component, right? But we don't have the normal stress in the x prime direction. And that's because, although you can't see it because it's such a mess, it does not show up in this free body diagram. So we need a different free body diagram, right? So we're going to cut it on the B phase. If I can erase all this. It takes forever to erase. So the second free body diagram is going to expose that value. Again, if I can erase it. All right. So now if we do a cut with this B segment, okay? So I'm going to now like take this and cut it. Oh, let's cut it like this, right? Cut it just like that. So now I have, I'm trying to make this bigger. Oops. So this is a cut along that line B. Again, this is the 30 degrees. On here, right, this is still, this is delta A, right? This face here is delta A cosine 30, or 1/2 delta A. And this is, I'm sorry, sine 30, which is 1/2 delta A. It's what I wrote, not what I said. And this face is cosine 30, or rad 3 on 2 delta A, right? So the traction on this component here, this is going to be a normal traction of sigma x prime delta A. And then acting along this face here is the shear component tau x prime y prime delta A. But we already know what that value is, but it's there. On this face, we would have the shear component acting in this direction. This is 25 megapascals delta A on 2. All right. And then the normal stress acting up of this 50 megapascals delta A on 2. And then on the left face, we have acting up this way, that traction, again, from the 25. So that's 25 rad 3 on 2 delta A, right? Stress times the area. And then we get the compressive force acting in this direction of 80 times rad 3 on 2 delta A, okay? And so again, like I said, we really want this component. So let's do, on this free body diagram, sum of forces in this direction, in the x prime direction. So we're going to do sum of forces in the x prime direction equal to 0, okay? So super quick. Again, I'll drop the delta A's. I get a sigma x prime on that face. I'll go to the top face. Okay, the 25 it's in the negative direction, and it's a cosine of 30, so it's negative 25 rad 3 on 4. All right. The 50 is a sine, so that is also in the negative direction, negative 50 over 4. Then we go on to this left face. So the 80 is, which component? This component here, right? We want that component. So that's going to be a cosine of 30, and that's actually in the positive direction. So it's 80 rad 3 on 2 times another rad 3 on 2, which is going to be 3 over 4. And then this component here has a component in the negative x prime direction, and it's a sine, so it's negative 25 rad 3 on 4, and all that has to equal 0, and that'll give you that sigma x prime is equal to negative 25.8 megapascals. Okay. And like I said, you can do sum of forces in the y prime direction on this free body diagram, and it'll get you tau x prime y prime, but we already received that, and it's not going to change. So that means that actually, if we were to do all that work, right, we would now know the stress components in this rotated coordinate system, right? So there you go. That's the little bit of material shown here. And we have a compressive stress in the x prime direction of 25.8 megapascals. All right. And then in the y direction, we also had a compressive stress. It was kind of small though, but it was like this. And that was, oh, I'm sorry, 4.1, right? And then we had a shear stress. It was a positive shear stress. So it acts in this direction like this, and then like this, and then like this, and then like this. And that value was 68.8 megapascals. All right, so very heavily dominated by the shear stress, whereas the initial state of stress, actually the shear stress was the lowest, okay? Again, if this material is going to fail, it fails with this stress state or with this stress state. Obviously, you know, what the components are don't really matter to whether it fails, okay? But there is this relationship between all the components, the entire stress state, that in a sense, they are equivalent, okay? It fails regardless, right? So sometimes people will say the stress is invariant under coordinate transformation. So it means that there's certain things that don't really change when you look at it from different orientations, okay? All right, so that's how you do it manually. It's kind of a lot of work, okay? And like I said, you can go through it, and I probably spent more time doing that than I really wanted to, but it is hard to just kind of half do the derivations, right? But you can see it's a little bit tedious, and it's the same approach every time, right? So you could be very much tempted to do this for a general case where we don't have numbers, just using sigma x, sigma y, tau xy, rotate it by some angle theta, which gives me sigma x prime, sigma y prime, and tau x prime y prime. And this is in the book, and I also posted derivation on that. And you could derive this set of equations. So in fact, in your textbook, this is equation 9.1, 9.2, and 9.3. And this derivation is exactly what we just did, all right? So it is no different, except we don't have numbers. It's all done in terms of letters. And so what do we have here? There's a little bit of manipulation because there's a half angle theorem that goes in there. But what do you got? Okay, on the left side, we have the things that we want. the stresses in the new coordinate system, sigma x prime, sigma y prime, tau x prime, y prime. On the right-hand side, it's in terms of all the stuff we know or the stuff that's in the prior stress state. So you can just do straight up plug and chug here, okay? You know these values, you know theta, stick them into here, and you immediately get the stress components in the rotated coordinate system, okay? So that's why I don't want to get too much in all those derivations. I think you can see that this is like a little bit easier, especially if you have this like in a calculator or, in MathCAD, right? It's almost trivial. Or you can put it in a spreadsheet too. It doesn't matter, right? All right. So do I do that the same way? So yeah. So if you plug this into, if you do the same thing, which we do here, and this is the same problem, just using those equations, yeah, we get the same values, right? We get the same values. I think it's supposed to be positive. Let me just check the shear stress. Oh yeah, actually that's right. Yeah, this is actually negative. That's the way it should be. So actually, I think I screwed up here. Oops. On this one, this should actually come out to be a negative, and this should go in this direction. Sorry, this direction's shifted. Oh, it's terrible. Okay. All right. Okay. Well, I guess I made one mistake. All right. So there you go. So that's a lot of just basically pretty simple freshman high school math. But it gives you the answer. Okay. All right. So again, I think this is probably the way I would solve these types of problems. Given a state of stress, find the stress components in a rotated coordinate system. I would just use the equations, right? They come about just from sum of forces. So the important thing about that is, again, it's the physical connection. That derivation tells you that, the stress components are not arbitrary, right? I mean, they're related through the equations of equilibrium. They have to be, right? And that's what makes it so if it fails in this orientation, it fails in this orientation, fails in this orientation, right? Fine. Okay. Fine. All right. So that's that. All right. What time is it? Yeah, I should stop. I know I should probably stop and do an example problem, but I just did one, I guess, even though I don't like that example problem. But let's talk about this other concept, okay? Okay, this is really critical. This is kind of interesting. So Otto Moore is a famous, I'll call him an elastician. I guess he would probably be considered more a physicist in the 1890s, 1870s, 1890s timeframe. He did a lot of work on, stress, continuum mechanics. And, this is back in a time where they did not have MathCAD, right? In the 1890s. They didn't even have CAD. Forget about MathCAD, right? So, even computing things like this may have been a bit troublesome, right? So there's this neat graphical trick that you can use that actually is equivalent to this. And in fact, when I first started teaching like 20 years ago or whatever, I wasn't really a big fan of Moore circle, but over the years, I've actually kind of appreciated a little bit more why Moore circle is actually quite useful, because it does allow you to very quickly see principal states and things like this. So I used to not teach it as much, but I actually do think it's more useful than I thought in the past. And it's one of those things, it's like Bernoulli's equation, or F equals ma. Like if you're going to call yourself a mechanical engineer and you don't know what Mohr circle is, people are going to call you out and say like, okay, I'm going to question whether you're really a mechanical engineer or not. Okay. It's just sort of one of those things, but it's basically a graphical method that they figured out in the 1890s that allows you to do this stress transformation. Okay. So I'm not going to go through the derivation. Again, I posted a video online and I got a PDF that goes through explicitly all the steps. But if we take these equations here and we kind of massage those, you can actually get them in this form. Now, I know there's some different variables here, but you can actually get them into this form. And if you look at this, this looks like the equation of the circle, right? So if you were to looks like, which is probably not too surprising because it's called Mohr's circle, okay? So you can see here, we have like an x squared term, y squared term equals a radius. So the x squared, right, this is kind of like x minus the center point squared plus y squared equals r squared, right? So the y doesn't have any offset. The y center is actually at y equal to 0, okay? That's what you get. And that's what you get if sigma average is defined like this. That's the center point. This is the x center point. All right. Obviously, the y center point is 0. All right, so it sits right on the x-axis. And this is the radius of the circle, okay? And what do we have here, right? Well, if you look at this, right, this is the average of the normal stresses. And right here, we have the difference of the normal stresses, you know, over 2, right? So that's what you get. So let's look at what this looks like visually, I think on the next slide, right? So I've just rewritten those things here, okay? All right, and here's a coordinate system. Okay, so if we have a state of stress, right? Let's see, how do we do this? There, okay, yep, very good. There's the state of stress. I forget exactly what pops up when I do these things. I made these slides like a long time ago. All right, so there's our given state of stress. So we have a normal stress in the x, y, and a shear stress. All right, so on the x-axis, I'm going to plot the normal stresses, and on the y-axis, I'm going to plot the shear stresses with this convention that if the shear stress wants to rotate it counterclockwise, it's positive. So let's first start on this face here, okay? All right. So if we look at this face, and I'm going to plot a point that corresponds to this face in this coordinate system. So it's a positive sigma x, right? There's sigma x. And this shear stress on this face wants to rotate it in the clockwise manner. So it's positive, it goes up. So that gives me a point right here, okay? So this is tau xy, all right? All right, now let's go to this top face, and I'm gonna plot another point. And actually, so again, the y is also a positive stress. Let's assume it's less than sigma x. So this value here is sigma y. All right. And same shear stress, but on this top face, it wants to rotate the cube in a counterclockwise manner, right? So that's why I went down a negative tau xy. And you're always going to see that because on every face, it's the same shear stress, but one pair of face rotate them, like on this face and this face. They always want to rotate it clockwise, and on the top and the bottom face, they're going to want to rotate counterclockwise. So you're always going to see this where you have a normal stress in the X and the Y direction, and then the Y component is going to be plus or minus the shear stress, okay? And actually you get the same circle regardless of which way you draw it, but technically this is the point corresponding to this face, and this is the point corresponding to this face. Now we could also do this back face here, and if we do that, we have a positive sigma X, and so that's here, and a shear stress that also puts it in the positive direction. So actually we get the same exact point. So this is also this face. And likewise, this point here is going to turn out to be identical to this bottom face. Okay. So actually for a given state of stress, we get 2 points. And that's what's shown here. Those 2 points correspond to the tractions, if you will, the stresses on the cube in that orientation. All right. All right. Now let's go back and look at this equation. This is the equation of the circle. And as I said before, this corresponds to a circle with this radius and is at the center point, sigma average 0, right? That's the center point. Okay, so what's sigma average? Sigma average is the normal stress in the X direction plus the normal stress in the Y direction over 2. It's the mean of those. Well, guess what? It's going to be right here in the middle. That's this. Oops. So that point right there is sigma average. Oops. And the Y coordinate is 0. So right there, that is the center of my circle. That is the center of my circle. All right. Now, let's look at the radius, okay? All right. So if you look at this, right, this is like, how do we compute radiuses? This is obviously like from Pythagorean theorem, where this is the radius, this is the Y component, and then here's the X component, right? Okay, so this is sort of the delta X. I'll do it this way. Let's call this delta X. Right, so this is the delta X, and this is the delta Y. Square them, sum them up, all right, and you get the radius, okay? All right, so fine. This is actually, why have I minus there? Oops. All right, so sigma X minus sigma Y over 2. All right, this distance here is sigma X minus sigma Y, correct? And then half of the distance is this leg. So this is sigma X minus sigma Y over 2. So that's that distance. And then tau xy is the Y distance. And so you can see actually right here, this is the radius, or likewise, this is the radius. Okay, so the circle contains these points. That's not too bad. So now we've got a circle. Well, I bet you if I push the button again, I'll draw a nicer circle. Okay, so this is more circle. Great, who cares? What does this mean? Each point on this circle corresponds to stress transformation. Okay? Each point on Moore's circle corresponds to a different stress transformation. Now, all those stress transformation things involve an angle. So this rotation here is actually 2 theta. Okay, so this point and this point here, that corresponds to the original given state of stress. Okay? All right. Now, if we were to look at a state of stress that's rotated from the original by an angle theta, that state of stress would correspond to the following, right? I would get a sigma x prime, a sigma y prime, or tau x prime, y prime, right? That would correspond to these points here. We've rotated 2 theta because all the equations involve double angle, right? And that makes sense too, because remember, this face here corresponded to this and this. So if we rotate 180 degrees from this face to this face, it corresponds to 360 degrees rotation when you multiply it by 2. Okay, so you get the same thing. This state corresponds to what's going on at this face, and this one is going to correspond to what's going on to this face. So this value here is going to be sigma x prime. This value here is sigma y prime. And this value here is tau x prime y prime. And those things can all be computed like geometrically, or in the old days, if you had a drafting table, you would draw this very accurately, and then you would just directly measure it with like a ruler, and you could get all these values without a calculator, right? Because they didn't exist. All right. So that's Moore's circle. Okay. So here's the method we do. You're given a state of stress. You plot the 2 points corresponding to the face. Either the front or back face. I'm sorry, either the right or left face. Usually I use the right, and then either the top or the bottom face. I usually use the top. If it's a positive, the x-axis is the normal stress, so that's pretty easy. The y component is the shear value, remembering that if the shear value on that face wants to rotate it in a clockwise manner, it's positive. If it rotates it in a counterclockwise manner, it's negative. Okay? And then you just draw the circle. Okay. So, okay, there's all that stuff. Okay, there's a fancy circle. All right. So let's look at our same example here, 9-1, and let's do it with Moore's circle. Okay? All right. So here's our state of stress. So here is the first face, okay? On that face, right? What shows up here? Oh, okay, nothing shows up. All right, good. On this face, right, we have the normal stresses. And then on this axis, we're going to have the shear stresses where clockwise rotation is up and counterclockwise is negative. All right. So this first face, the normal stress is compressive. So it's a -80. I think each one of these ticks, let's make each tick 20. So this is 20 minus 20 minus 40 minus 60. This is -80 right there. All right. All right. All right. That's the X component. And then here we have the Y component is the shear value. It's 25. But it's going to rotate it in a counterclockwise manner, okay? It rotates the cube in a counterclockwise manner. So it's a negative value, so it's -25. So here's -20, -25 is about there. So this is going to be -80, -25. That's 1 point on Moore's circle corresponding to this right face. Okay. Now let's do the top face. Again, you could have done the left face and the bottom face. but they give you the same points. But so I always do the right face and the top face. So now let's do the top face. Okay, top face. Normal stress gives me the X component. It's a positive 50. So 20, 40, 50 is about here. Okay, so that's positive 50. And this 25 megapascal shear stress wants to rotate it in a clockwise manner on that face. So I go up 20, 25, that'll put me about here. Okay, so that's the point 50, 25, right? And those are 2 points on the circle. The center point of the circle, you know, we can draw the line that connects these. All right, but it's pretty easy to compute the mean of this. So minus 80 and 50, right? You add those together, you get minus 30. Half of that is 15. So actually the center point should be right kind of here at 15, right? And then we can draw the circle. Okay, the radius of the circle, let's figure it out. So that the center, the average is minus 15 megapascals, right? And to get the radius, it's going to be the square root, this distance here, which is going to be, you can either just do 50, you know, this distance here is 50 minus 15, or I'm sorry, so that's 65. And this distance here is 25. So the radius is going to be 65 squared plus 25 squared. I don't really even need to use those equations before. I mean, I just compute it geometrically, but you can use equations. You get the same value. If you were to do that, I get a radius of 69.6. Okay, so that's the radius. So that means the top of the circle is going to go up, you know, the radius. So that's 20, 40, 60. So it's about here is the top of the circle. 20, 40, 60. There's the bottom of the circle. So just to quickly kind of sketch it, it's going to work. Right. So there you go. You get a circle, right? Okay. You get a circle. All right. All right. Now that's all well and good. And like, you know, we could figure out, you know, like I said, if we wanted to figure out this 30-degree rotation, right? We want to get the stress components at 30 degrees, right? So we would actually, if this is 30 degrees, the way it's shown, we're actually rotating it negative 30 degrees. So we would rotate this negative 60 degrees, which is about like, I don't know, it's about like there, right? And so that'll give us the components on the new face. This would be, this angle here is now 60 degrees, okay? Because we're rotating at negative 30 degrees. This would be sigma x prime, and this would be tau x prime y prime. So this point here would have the values of sigma x prime and then tau x prime y prime. And you can figure out the direction, you know, you get. It's obviously going to go, it's a negative value, so it's actually going to make it counterclockwise, so it's going to go that way. This value here would be on the top face, so it has a negative compressive stress. This would be sigma y prime, and then likewise the shear stress going that way, right? And that's what you get. And those could all be computed graphically, okay? All right. But really where this becomes even more important is when we talk about the calculation of principal stress and the max shear stress, okay? And so let's talk about what principal stress is, right? So principal stress, right, here's a Mohr circle, okay? So here we've got the normal stress, and then we here have the shear stress, right? Okay. All right, so we have some general state of stress indicated here. Okay. And so we have a sigma x in this direction, right? Let's assume this is sigma x. And this value here is tau xy, and it wants to rotate it on the sigma x face in a positive direction, so that means it's going this way, and then this way, and this way, and this way. And then the y stress, the normal stress in the y direction is compressive, so we get something like this, right? All right, so I mean, I'm obviously, you know, you're given values here, right? But this is the Mohr circle corresponding to it, right? This point here is sigma x, tau xy. This is sigma y, which is negative tau xy. All right, okay. And every point on this circle corresponds to a different stress transformation. It's looking at it in a different coordinate system, okay? There are a couple of points here that are rather interesting. If we were to rotate it, like let's do this one, let's rotate it down into this orientation. So this is 2 theta, right? So let's say we were to rotate it, that's what I try to do here. I'm rotating it clockwise, right? By 2 theta. And actually, I do this the wrong way. These should actually go this way. This one should be going this way. This should go this way. And this one should go this way, just to be correct. This one should go this way, and this one should go this way. The way I drew it. Okay. This angle here is, well, let's do this one. So we're rotating here by this angle, theta. Half of this angle, because every angle in Mohr's circle is twice the physical angle, okay? All right, so 2 theta. What do we get? We get a stress state here and here. The interesting thing about this stress state is there is no shear stress. Only normal stress. All right? And that's going to always exist. You're going to get a circle, right? Even if you have some weird degenerate case where, you know, the normal stresses are 0, you still get a circle, okay? So you're going to get a circle, and it will be centered on the x-axis. So there's always going to be a state where there are no shear stresses. That is what we call the principal state stress. The principal state stress is the state of stress where there is no shear stress. All right? Only normal stresses. And here you can see, here's one normal stress and here's the other normal stress. So if we rotate this face down to here, so this value here, we normally call sigma 1, and this one we'll call like sigma 2. These are the principal stresses. And it's principal like the principal of your school, your pal. Not the principal, right? So those are the principal stresses, right? And you can see whether you start with this orientation or this original orientation or whatever, you will always get the same principal stresses. These are invariant. So that's why they're kind of important. So although there's an infinite number of orientations that we can report the stress state, there's only one unique set of principal stresses. And so that's why it's important, okay? And so there they are. And how would we get those? Well, if you look at this, we know this is sigma average, and this is a radius, and this is a radius, which we're going to calculate using Mohr circle. So the normal stresses are sigma 1 is sigma average. Well, let's just do it this way, because which one's sigma 1 and which one's sigma 2 is sometimes arbitrary, right? So I'm going to just do sigma 1 and 2. The principal stresses equal the average stress, right? The center of your Mohr circle plus or minus the radius, okay? So in this particular case, we would take this face here, rotate it half of this angle, get you down here, and we would get sigma 1 on this face, which is pretty close to sigma x, right? But you would get sigma 1 there and sigma 1 there. All right. And then this point here, which is the top face, again would rotate up or rotate to this orientation. And that would give me sigma 2, which again would be compressive. All right. And you can calculate those. All right. And there's no shear stress. Now we can also get the angle, right? Because we know this distance here, right? And we know the height, okay? So remember, this distance here is sigma y minus sigma x over 2. It's like the absolute value of that, right? So the tangent of 2 theta, and this angle here we usually call theta p because it's the angle that gets you into the principal state, equals the rise, which is tau xy over sigma y minus sigma x over 2. Okay, so you just take the A tangent of that and you get twice the angle. Okay, so you can easily figure out not only what the principal stresses are from Mohr circle, you can also figure out what's the orientation. We can get this angle theta that puts you into the principal state. That's a little harder to do from those 3 equations, 9, 1, 2, and 3, okay? So that's the principal stress. Really important. Most material failure theories are in fact written in terms of the principal stresses, okay? And let me just do one last bit. Max shear, same point, right? This is the same thing, right? So it's Mohr circle, right? What about this point where we're up and down, okay? This is the point where we have the max in plane shear. All right. Now, in this particular state, right, this is if we rotate 2 theta shear. What you're going to see here is we get tau max, right? Tau max. And what's that going to equal? That is just the radius of the circle, okay? And there is also, it's not like the principal stress. It's not like it's only shear because you have a normal stress value, which is the average, okay? So if we rotate that off a Mohr circle, right, this angle here is theta s, and we would get the normal stress, which is the same on all the faces of that average stress, and then the shear stress is like the following. I don't know why they did that. That's weird. Well, if we do it from here, we go up here, so that face would rotate like this. So if that face is a positive, it's going to go actually this way. And this is tau max, which is equal to the radius of Moore's circle. Okay? All right. That's the max in-plane shear stress. Now, there's actually another case where you will get a different max shear stress. This is the absolute, I shouldn't say max, this is the maximum absolute shear stress. So if we have a Moore's circle that looks like this, let's assume that both we have a positive X and Y stress, right? Sigma X, sigma Y, and then a shear stress like follows. Right? So this point here is sigma X, tau XY, and this point here is sigma Y minus tau XY, right? So sigma X and sigma Y are both greater than 0, or could be both less than 0. Look at the same situation. All right, you might be tempted to say, okay, fine, this value here is the maximum shear stress. Well, that is the maximum in-plane shear stress, but there actually is another set of Moore's circle. And this has to do with the fact that there is also stress transformation coming in and out of the board. We haven't talked about rotating anything other than in the plane. So there still is the zero stress out of the board. So there actually is a normal stress coming out of the board. This is like a sigma z, and if it's a planar state of stress, that corresponds to 0. In fact, that puts a point on Moore's circle right there. So you actually have this little Moore's circle as well as this bigger Moore's circle, which I know I drew really poorly. And you can see in this particular situation, this value of tau max is going to be greater than this value. That only happens when you have Moore's circle, the normal stresses are both positive or they're both negative, right? And this is the radius of your Moore's circle, but tau max is really this larger radius, which is going to be, if in this case, this is sigma x, so the radius of this bigger circle is going to be sigma x over 2. Now, if this was sigma y, it would be sigma y over 2, okay? That's actually the maximum value of shear stress for that material, and it actually is a rotation that's not quite in the plane. It also involves a little rotation out of the z-axis. It's a little difficult to visualize, so we don't really go through it, okay? But if you have both normal stresses, either positive or negative, that's the case. Now, if you look at the previous example here, we had a positive and a negative value. So the 0 point for the out of plane stress is there. And so the two Moore's circle that correspond to the out of plane transformations are like that. They also have max in plane shear stresses, but they are going to be less than the one for the in plane Moore's circle. So in this particular case, this one is equal to the max absolute as well. All right. So there's several problems in the textbook that have you computing these things. The easiest way to do these is to draw Moore's circle. So if you have problems involving getting the principal states or the max shear, max absolute shear, I think it's always easier to do Moore's circle. Although the book does give you some explicit like equations for doing it. You can use those too, but sometimes it gets a little confusing if you have to do this max absolute versus the max in plane, okay? And I went over, and that was a lot of material, but please read it over. It's not that hard, but try to remember the concept that we're looking at the same state of stress, but in different coordinate systems. And these concepts of max shear as well as principal stress are really critical when we start talking about, does our component actually fail? We've simplified this in the past because we just say, okay, it fails if the normal stress exceeds this, but that's not really how materials behave. It's kind of like a fake way we did it to simplify it so we didn't have to talk about failure theories, right? In design, you're going to talk about failure theories, okay? All right. I will discard these. All right, that's it. I'm going to let you guys go.